a compound composed of only carbons and hydrogen atoms. So hydrocarbons can be then subdivided in two groups: saturated hydrocarbons. Those are hydrocarbons containing only carbon-carbon single bonds. So basically, each carbon having four single bonds, all sigma bonds, sp3 hybridized. On the other hand, another group are the unsaturated hydrocarbons. Those contains double or triple bonds. It could be one or both together, different combinations. So alkanes are saturated hydrocarbons, as I just said, sigma bonds, all sigma bonds, four single bonds, sp3 hybridization. And they are also considered aliphatic hydrocarbons. Okay. You will also see in organic 2 aromatic hydrocarbons, which are benzene derivative, but it's not the purpose of this class to discuss this group of compounds. Okay, so here are the common names for the simplest hydrocarbons containing from 1 to 10 carbon atoms. And here we have from 11 to 20. So as you can see, so two things here. All of these names, you can see they end in the same, with the same name, ane. So that's from the alkane. So that's the ending, and then the prefix of the name indicates the number of carbons. So meth is one carbon, methane, eth, two carbons, ethane, prop, three carbons, propane, bute, four carbons, butane, pentane, five, hexane, six, heptane, seven, octane, eight, nonane, nine, and decane, 10. Here is a list for the remaining from 11 to 20. You must be familiar with all these names, and as you practice in the class, you obviously will remember this very easily. Okay. So these are the names, as you can see, for the linear hydrocarbon. That's a carbon chain that is absolutely linear, as you can see here. Okay. So CH3, CH2, 6, CH3, all are linear hydrocarbons. That's the name for them. So as I said before, for hydrocarbons, all carbons have four sigma bonds. This is basically the way you can tell that they have a sp3 hybridization, and because of the hybridization, the bond angle in between the bonds on the carbon is 109.5. The geometry is a tetrahedral structure. For every carbon on an alkene, that's the case. Another really relevant feature about alkanes is that because every carbon has only single bonds, there is free rotation around the carbon-carbon bonds. Okay, so for example, around this carbon-carbon bond, this molecule can rotate over here. Around this carbon-carbon bond, the molecule can rotate over here. Same thing on this side over here. So the summary of this is that because of this free rotation around the single carbon-carbon bonds, the molecules can be in many different shapes or 3D arrangements, which we will call conformations. So that's a distinctive feature of alkenes: free rotation in around every carbon-carbon sigma bonds, which allows them to have multiple conformations. And lastly, because of the saturation, their general formula is CN2N plus 2. So all alkanes will respond to this molecular formula. For example, we have here hexane, 6 carbon atoms, and it's 6 times 2, 12, plus 2, 14. So the molecular formula for hexane is 6C6H14. So as I just said right now, because in alkanes every single carbon and in cycloalkanes as well is sp3 hybridized, they all have tetrahedral geometry, and obviously they have multiple conformations. This is just to show you, and this is something we already covered in chapter 1, we can also draw alkanes in line and angle formula. So in this case, as you know, we don't show hydrogens, and each vertex is a carbon. So this is propane, linear alkane with 3 carbons. This is butane, linear alkane with 4 carbons, and here is pentane, linear alkane with 5 carbons. You guys know at this point, once again, how to draw organic molecules in line and angle notation. Now, as we increase the number of carbons, for example, here is an example for butane, 4 carbons and a linear, so they are connected linearly. Here we have another alkane in which there are also 4 carbons. However, the connection between the carbon is different. So there is one connected to the carbon in the center. So here is the line and angle for both of them. So the molecular formula for this compound for both of them is C4H10. So two compounds having the same molecular formula, we call them isomers. So I want to emphasize that, okay? Same molecular formula, they are isomers. Now, in this particular case, they have the same molecular formula, different connectivity in between the atoms. So the connections here is linear, the connection here is different. So two compounds having the same molecular formula and different connections in between the atoms, we call them constitutional isomers. So constitutional isomers, importantly, they are different compounds and they do have completely different physical and chemical properties. You can imagine how, as we increase the number of carbons in an organic compound, in an alkane, the possibilities for constitutional isomers also increases substantially. For example, for alkanes with 10 carbons, we could find 75 different constitutional isomers, 75 different compounds with different connectivity in between the atoms. Alkanes with 25 carbons, we can find an stunning number of above 36 millions of constitutional isomers. Once again, remember guys, the constitutional isomers, same molecular formula, different connectivity. They have different physical and chemical properties. They are different compounds. So because we have compounds with the same molecular formula and they are different, we need to find a way to distinguish them. And that's the reason why compounds do have names. So we can name these compounds to differentiate them. And we will learn how to name them according to the rules of the International Union of Pure and Applied Chemistry. So that's the nomenclature of the organic compounds. As I just said right now, the reason for that is because each of them is a different compound, so they must have also a unique name. So let's learn the IUPAC rule for naming organic compounds. So the first thing that you need to understand is, as I said before, the prefix in these compounds will tell you the number of carbons. And this is something that you guys just need to know. Meth1, F2, Prop3, But4, Pent5, Hex6, Ept7, Oct8, Non, 9, Dect10. And here you have a list from 11 to 20. Okay? And the suffix "ane" specifies, in this case, that we are talking about alkanes. So saturated hydrocarbons. If you said methane, so that's an alkane with 1 carbon, CH4. If you said hexane, that's an alkane with 6 carbon. So the way to name the compounds, or to name them, first of all, we have to determine how are we going to choose the parent name of the compound. And the parent name of the compound will be determined based on the longest carbon chain of the compound. To this chain, you can have them different substituents bonded to it. These substituents could be, at first, functional groups, which you have already studied in chapter 1, but they can also be alkyl groups. An alkyl group is basically a substitutions which is derived from removing a hydrogen from an alkane. So basically, alkyl groups are groups bonded to the parent chain having only carbons and hydrogens. Okay, and the general way to symbolize them is using the letter R. Okay, so if you see a carbon chain and an R bonded to it, that means that it's a genetic name for an alkyl group. It could be any alkyl group. That's what R means. So here is two examples. So once again, alkyl groups comes from alkanes from which we remove a hydrogen. So for example, here is methane, CH4, meth for 1, alkane, CH4. We remove a hydrogen, we are left with CH3. This carbon, once again, is bonded to 3 hydrogens, and the fourth bond is to the carbon chain. Don't forget that. So because it's the alkyl group derived from methane, we call it methyl group. Meth from 1, Yl from alkyl, methyl. When you have 2 carbons, that's CH3, CH2 bonded to the parent chain, that's the ethyl alkyl group. It is very important to know the names of the alkyl groups because you will need them to name the organic compounds. So when you're talking about the linear alkyl groups, so we have methane, which is a single carbon, methyl, ethane, ethyl, and then from propane, if it's from the first carbon, the alkyl group is propyl. And you should also be familiar with the abbreviation for methyl, for ethyl, ET, for propyl, PR, the first letter in capital letters. But as we increase from 3 to 4 and 5, then once again, then we have different possibilities on how to attach this hydrocarbon group to the parent chain. For example, propyl has 3 carbons. If we bond the propyl, if it's bonded to the main chain from the first carbon, that's a propyl group. However, when it's attached from the carbon from the second carbon, then that it will be or it is known as the isopropyl group. So any group, any alkyl group ending in this CH, CH3, CH3 will be called iso. And then after it will have the number of carbons. So iso, and because it has 3 groups, propyl. 3 carbons, I'm sorry. So if we can then go to the next alkyl group with 4 carbon, that's butyl. If it is bonded as is shown on the slide here, from the first carbon, from the primary carbon, that's butyl. So I'm gonna stop here and quickly tell. We can also classify carbons as primary, secondary, tertiary, and quaternary, depending on how many carbons are bonded to the carbon you are actually classifying. So in the case of butyl, this carbon is bonded to just 1 carbon, that's primary. This carbon is secondary, this one is secondary, and this one is primary. But you can also have 4 carbons that are actually bonded to the parent chain in this way. So these two, you see the difference. So in this case, we have a primary carbon here, right? And then a group ending in CH bonded to CH3. So remember, this is iso. And because there is a total of 4 bonds here, this is isobutyl. So iso because it's ending in this CH3, CH3. But because it's 4 carbons butyl because it's an alkyl group, isobutyl. When it's bonded through the second carbon of a linear chain, because this carbon is secondary, this group is named sec-butyl. But you can also arrange four carbons in this way. 3CH3 bonded to a carbon. This carbon is tertiary, is bonded to 1, 2, 3 carbons. Because of that, we call this the tertiary from tertiary butyl, total of 4 carbons, and this is an alkyl group, terbutyl. So as a summary, for 3 carbons on an alkyl group, we can have propyl or isopropyl. For 4 carbons, you can have a butyl group, an isobutyl, sec-butyl, or terbutyl. If you go to pentyl, then the number of possibilities increases. So the nomenclature will include using these names for naming the organic compounds, so you guys definitely should be familiar with these alkyl groups. Okay, so let's go now that we learn a little bit about alkyl groups. Let's try to understand the basic rules from the IUPAC to name organic compounds. So the first rule, so the first step whenever you're going to name an organic compound is to identify the longest continuous carbon chain. And that would be the name of the compound. So here is an example of a compound. Once again, guys, you do not want to be confused on how the compound is presented, okay? So here is this compound. We have 1, 2, 3, 4, 5, 6 carbon. This is one possibility for a carbon chain, but continuous carbon chain also is over here. 1, 2, 3, 4, 5, 6, 7. Because we want to identify the longest, so this is the longest carbon chain in this compound. So this could be the one giving the compound the parent name. Because it has 7, the parent name is heptane. Now we need to look how do we name the substituents to the parent chain. So the second rule is once we have determined the parent chain, the longest carbon chain, we need to number the carbons. Obviously, you can assign number 1 here on the bottom or number 1 on the other end of the carbon chain. So what is the criteria for that? So we number the carbons in such way that the substituents will get the lowest possible number. So means basically is if we assign the number 1 to this end here, 1, 2, 3, the methyl group will be attached to carbon 3. But if you were to assign number 1 to the other end, then the methyl group will be in carbon 1, 2, 3, 4, 5. Because we want to always assign the lowest possible number to the substituent, we will assign the number 1 to this end over here. Once we have assigned number, we just need to name the compound. So we know in position 3 that is a methyl group, so this compound will be 3-methyl heptane, which is the parent name. If you have 2 or more substitution into the parent chain, then you will use the lowest possible individual numbers. And when you build the name of the compound, you will have to order them alphabetically. When you decide the alphabetical order, it's important to disregard multiplying prefixes such as di, tri, etc. So let me give you an example. Okay, here we have a compound to name. First step is to find the longest carbon chain. The longest carbon chain is in red, and it has 8 carbons. So Second thing is to assign numbers. We can assign number 1 to the carbon on the left or number 1 to the carbon on the right. The criteria for that is to assign the lowest possible number to the substitutions. So in this, if we assign the number 1 here, the first substituent will be in position number 2. If we were to assign the number 1 on this side, the first substitution will be in position number 3. Because we want the lowest possible number, the number 1 will be the carbon on the left. So basically, you want to number 1 the carbon that is closest to a substituent. That's the rule. So once we number the chain, then we have the substituents. In position number 2, we have methyl. In position number 6, we have ethyl. We ordered them alphabetically. And then the name of the compound is 6-ethyl. E goes first. 2-methyl octane, which is the patent name. So you can also have a case in which you have two substituents on the same carbon. Here, example. The main carbon chain is in red. We assign number 1 to the carbon on the left because it's closer to the substituents. Now we have a methyl and an ethyl group. They're both on the same carbon. We ordered them alphabetically. So the name of the compound would be 4-ethyl, 4-methyl octane. Another scenario could be to have the same substituent in the carbon chain. So here is an example. The main carbon chain has 6 carbons. We need to number the carbons. We assign number 1 to the right because it's closer to the substituents than the one on the left, so that will lead to lowest number combination. In position 2, we have a methyl, and in position 4, we have another methyl. So in this case, we do not say 2-methyl, 4-methyl. So you say 2,4, 2,4 dimethyl hexane. Here is another example. Main carbon chain has 7 carbons. We start numbering from the right side because the right side is closer to the first substituent. So the combination of substituents here could be, if we start numbering from the right, 2, 4, 5. Whereas if you start from the left, would be 3, 4, 6. That's higher. So we start from right. We have 3 methyl groups, 1 in position 2, 1 in position 4, 1 in position 5. So that could be 2, 4, 5 trimethyl heptane. Another scenario is when you encounter a compound in which the parent chains, or to select the parent chain, you have 2 carbon chains with the same number. So here is an example. In this compound, you have 1, 2, 3, 4, 5, 6, 7. This carbon chain has 7. 1, 2, 3, 4, 5, 6, 7. This carbon chain also has 7. So we have 2 carbon chains with 7 carbons, and we need to make a decision on which one would be the parent carbon chain. The criteria would be the one having more substituents attached to it. So the carbon chain on the left has 4 substitutions, 1 in position 2, 1 in 3, 1 in 4, and 1 in 5. Whereas the one in position on the right side has only 3 substitutions, 1 in position 2, 1 and 1 in 4. So the parent chain would be the one in red because that's the one with a higher number, with a greater number of substituents. So once we know which one is the pattern chain, we assign numbers. Obviously, in this case, the number 1 is a carbon on the right end because it's closer to the substitution. So in position 2, we have a methyl. In position 3, we have a methyl. In position 4, we have a propyl. In position 5, we have another methyl. So we say 2,3,5 trimethyl 4-propyl heptane. So in position 2, 3, 5, we have 3 methyl groups, 2, 3, 5 trimethyl 4-propyl 1, 2, 3 carbons heptane. Remember, the letter for the alphabetical order here is the M from the methyl because we don't consider the multiplying prefixes. This is not taken into account for the alphabetical order. So the M goes first and then the P, okay? So another case that you can find is when branching takes place at equal distance from either end of the carbon chain. So here is an example. We have in red the longest carbon chain, and now we have to decide where to assign number 1 or number 2 or number 6. If we assign number 1 on here, next we have a methyl here, next we have a methyl. So the first group is at the same distance from both ends. So to make a decision, then we need to look for the second group until we find the first point of difference. So in this case, because we only have 3 groups, the first 2 is equal, so we go to the third group. The third group is closer to the right side, therefore we assign number 1 here. Once we assign the number 1, 2, 3, 4, 5, 6, we have a methyl in 2, another in 3, and another in 5. So 2, 3, 5, trimethyl hexane, which is the pattern carbon chain. Okay, so here is an example. Once we have learned all the basic rules, here is an example for naming a compound. First thing, as I said before, we need to find the longest chain. So let's just look at different possibilities. So here we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 4, 5, 6, 7. So clearly, the longest chain is the one in purple on the slide. Secondly, we have to assign the numbers. So the number 1 and in either the top or the bottom end carbons. Because we want the lowest possible number, we will assign the number 1 to the carbon that has closest the substituent. So if we place the number 1 here, we have a substituent at carbon 3. If we place it over here, it's at carbon 4. So there clearly, this will be where we will find the correct numbering. So because the number 1 will be on the end carbon, which is on the bottom, the substitutions will be in position 3 and 4. And in position 3, we have a methyl, and in position 4, we have another methyl. So to name this compound, we have now 3,4-dimethyl heptane. Okay? The longest chain, number 1 here because it's closer, 3,4, same group is methyl, so 3,4-dimethyl heptane. Here is another example. Look for the main carbon chain. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So far 8 is the maximum number. 1, 2, 3, 4, 5, 6. From here, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So clearly, this carbon chain here will be the longest. As I said, this is a 6-carbon chain. Here is an 8-carbon chain. It is another 8-carbon chain, which is the same as if you start from here. So you have to look at all the different possibilities. The longest is the 9 one. Okay. Parent name will be nonane. Now let's assign number to the end carbons. This carbon on top has a substitution in position number 3, 1, 2, 3. The carbon on the bottom also has a substitution in position number 3, 1, 2, 3. So that's the same. We need to find a point of difference. The next substituent is closer to the carbon on the left, 1, 2, 3, position 4. Therefore, the number 1 will be assigned to this carbon over here. So once we have assigned the numbers, now let's look at the substituents. Position 3, we have a methyl. Position 7, we have a methyl, so we will have 3,7-dimethyl. And in position 4, we have an ethyl. Now to build a name, we just need to order them alphabetically. Remember, the di prefix is not taken into account for the alphabetical order. So it could be ethyl and E versus M from methyl. So the name of the compound that would be 4-ethyl E first, 7-dimethyl nonane. So that's how you basically build the names of alkanes. So you can also have common names for alkanes. Okay. So as I said, the linear 4-carbon chain is named butane. Iso indicates a chain that terminates in this group, CH-CH3-2, like this one over here. Neo indicates a chain that terminates in a tertiary carbon with 3 methyl groups. So this is butane. Here we have an ending in the iso because the total number is 4. This is isobutane. Pentane, ending in iso because it has 5 carbon, isopentane. Ending in a tertiary carbon with 3 methyl group, that's neo. Total of 5 carbons, neopentane. So these are common names that you guys have to know. As I said before, carbons can be also classified into primary, secondary, tertiary, and quaternary. Just based on the number of carbons bonded to the other carbon. So a carbon bonding to just one carbon is a primary. Secondary carbon is that bonded to 2 carbons. Tertiary carbons is bonded to 3 carbons. And a quaternary carbon is bonded to 4 carbons. Obviously, hydrogen is bonded to other carbons, that's primary hydrogens, secondary hydrogens, and tertiary hydrogens, okay? Same rule applies. So that's something I had already explained before. So here is an example. For example, for propane, we have 2 primary carbons and 1 secondary carbon, bonded to 2 carbons. In methylpropane, we have 3 primary carbons and a tertiary carbon. In 2,2,4-trimethylpentane, we have a primary carbon here, another one and another one, 3 primary carbons, quaternary carbon bonded to 4 carbons, secondary, tertiary carbon, and 2 primary carbons. Okay, guys, apparently there was a problem. So I was saying here that I wanted to also discuss about cycloalkanes. I apologize, this Blackboard is giving me a lot of issues recording these videos. So cycloalkanes, the general formula is CnH2n. So cycloalkanes is basically saturated hydrocarbons that are cyclic. The most common are the 5 and 6 member rings, which are cyclopentane for 5 and cyclohexane for 6. To name cycloalkanes, basically you add the prefix cyclo to the name of the open chain alkane containing the same number of carbons. So that's why how I said when it's 5 is cyclopentane, 6 cyclohexane. If you have a substituent, you only have to uh, name the substituents. You don't need to give it a number because it's just one. When you have two or more, I'm sorry, when you have only two substituents, that could be the number one. And if you have three or more, you basically assign them the lowest set of numbers. Once you have them with the lowest set of numbers, you order them alphabetically, exactly as before. So here is an example of cycloalkane with 5 carbons, 1, 2, 3, 4, 5. That's cyclopentane. You have one substituent, 3 carbons. So remember, this is isopropyl. So the name of this compound will be isopropyl cyclopentane. So with that, I am ending this video. So nomenclature is a lot of practicing and practicing. So you guys need to do a lot of problems to be familiar with how to name organic compounds, in this case, alkanes. Thank you.